And without further ado, let me get into the main topic of this talk, which is image processing and a problem of Bourgain-Brezis. The path of this talk is a little bit convoluted, so I will try to slow down at certain points, and I will start the talk with a motivation from image processing. Assuming that most of you are not familiar with the technicalities of image processing, I will allow myself 1 or 2 slides for introduction, and here it is. So images, black and white images, are in fact two-dimensional signals. And here's a typical image that I will refer to. It's essentially a mapping from a domain. In this case, it is a square in R2 into R, positive R. And this mapping is essentially a mapping which measures the intensity of pixels that we see. It's the intensity of pixel in grayscale varying from 0, which is dark, to 255, which is the brightest pixel. And what we see really is a collection of these intensities in the many pixels that are scattered in this square. I want to emphasize this is very important. Some of you may have seen already that images are nothing but two-dimensional signals, but it's very important to compare what we see on the left and how the signal looks like in 2 dimensions. It's nothing but a smooth function. If at all, what we see are edges, which are the most noticeable here, right? But these edges are not well defined and they are not in sharp distinction from the rest. So we have a collection of edges and then other aspects of the image. And we have something which is, we have to consider an image, this function f, as something which is reasonably rough. Okay, so what do we do in image processing? Let me focus on the problem of restoration. First of all, we will postulate that an image is a function in L2 omega. First objection is, I just told you that this function is bounded by 255, but for reasons that will become clear later on, we will adopt the general framework in which images are postulated to be objects in L2. What are the main features of images? We just saw, for example, edges or textures, and usually they are sought in a smaller space than L2, denoted here by capital X, but it's not exactly clear what should be this X. In addition to the main features in images, there are some spurious features like noise or blur, and they will be modeled by quantities in a larger space, Y, larger than X. And our problem is to have a model which takes the smaller, the true parts of the image in X into Y, where we have a noise or texture which lives in the difference in between. And the problem of image restoration is to de-blur or to remove the noise and so forth. So here's an example. I will refer to this example to other examples, and I apologize, this is somewhat politically incorrect. However, these computations were done in the past and they are very important. So we will not look at the content, but we will just see a canonical example for an image. And clearly this is a blurred image. Why? Because we see that this is a blurred image. And the idea now, the problem is that if we have a blur image, what is the blur image that we observe? It's not the image itself, the clean image U, but it's the clean image plus some blurring or some another operator that makes it less clean, plus possibly noise. And what we really observe is this little f. So we observe the quantity on the right and the quantity on the left, and we want to restore or to recover the clean image on the right. This is our problem. Going from the observed to the source, in this case of the image, and this is clearly an inverse, an ill-posed inverse problem. And one way to address the class of inverse problems is to introduce a variational formulation, and here it is. Given the little f that we observe, and given some operator that we have to agree, which is the blurring or the noisy operator, script L, what we try to do is to minimize the residual, the difference between what we observe and an unknown U measured, this, let's call it the residual here. This residual will be measured in Y, the larger space. And in addition, we take, we want what we recover to lie in the smaller space X, which is the space of true images. we try to minimize this weighted sum. The minimizer will be denoted by U, and it depends on a parameter lambda. If we get this capital U lambda, then we can say that what we observed is in fact some operator operating on the true image, U depending on lambda, plus a residual. I should mention that the parameter lambda is in fact not a parameter. In fact, it is a scale. It really means that when we have an image, we extract the edges or the important feature in the image up to scale lambda, and the rest is captured by the residual. So this is a general framework for solving an ill-posed problem. And I would like now to bring a concrete example for this kind of variational formulation for denoising images. And it brings us to the model of Rudin, Osher, and Fatemi from 1985 or 95. It was many years ago, I forgot. And the idea is the following. We will ignore now the case of a blur. We will just take into account the fact that the images have noise. So in fact, we observe an image F and we want to compose it to the original clean image, capital U at scale lambda plus a noise. The model of Rudin, Osher, and Fatemi, which has no L is the identity, is just the residual, suggests to make this decomposition subject to the following choices. Since we have noise, we will measure everything in L2, and it makes sense, therefore, to measure everything in L2. But the true images will be measured in the space of bounded variation functions. In fact, this original paper from 1985, I forgot the date, was the first to point out the importance of the space of bounded variation in this context of image processing. And now what we are looking at, therefore, is the minimizer, where we try to minimize the residual in L2 squared plus the total variation of U. And this minimizer will be denoted by U lambda. And this is the beginning of my lecture. The ROF, the so-called ROF algorithm, led to hundreds of papers and works. It had a huge impact in this field of image processing. And what I would like to propose to start the discussion here is with a concrete solution of the ROF variational statement here. So I will try to solve once and for all in this variational statement in a concrete way, which will be explored in a second, and we will see how we can do it. Since we have a minimization statement, every minimization statement has a dual version, and the dual version in this case is, instead of trying to find this a function of two variables U, we try to find the maximizer, which is a two-vector, capital W, mapping R2 to R2. And the maximizer should maximize the following variational statement. It should maximize all the two vectors uniformly bounded by one of the integrand written here, plus another term depending on lambda. In fact, if we find the maximizer, then its divergence will lead us, this is exactly the relation to the ROF minimizer. So we have to find the maximizer. Of course, we notice that this maximization problem, the second term just depends on the data, we can ignore it. There is also a minus sign, so we can ignore that. So in fact, the idea is to focus on this first term, and then we should try to do the following. We'll take the image, which is an L2, we will write it as a divergence, and then the whole integrand here will be a divergence of something which I called age. So in fact, age is nothing but square root lambda U minus some coefficient of W. And what we try to find is a minimizer, not a maximizer, because of minus sign of the following statement. The integral of div h squared subject to pointwise bound, the L infinity bound here is converted in terms of h to the L infinity down there. That's it. So in this sense, what we have here is in fact an obstacle problem. Why an obstacle problem? We try to find a minimizer, which is an L2 minimizer subject to a pointwise constraint. So the obstacle problem is a wide topic. I will not dwell any further. I just want to point out that I took the ROF problem and I converted it into an obstacle problem, namely try to find the minimizer of this L2 integrand subject to a pointwise constraint. If we find the minimizer for the obstacle problem, then our u lambda is simply given by 1 over square root lambda times its divergence. So in this sense, we have a concrete solution, or at least we converted one problem into another more familiar territory, except for one small point. Here, in order to do that, I took the image F, which is an object in L2, and I wrote it as the divergence of U, and it is important that the U will be uniformly bounded. So it remains to find the bounded U, uniformly bounded U, such that its divergence equals to F. Once we have that, then the recipe that I have here will follow. So what about this small problem? Given the L2 object F, write it as the divergence of something which is uniformly bounded. This is the problem. To simplify matters, I will take it now on the torus rather than the square. The ds below means that we have zero mean, so it is really F can be written as the divergence of something. And we try to find a uniformly bounded U such that d view equals to F. This is the small leftover from the ROF problem. So here is the equation, and here's the constraint. And let's think a little if we can solve it. So the first attempt is, of course, this problem has many solutions, let alone we can find a solution which is uniformly bounded. Let's try the Helmholtz solution, which is the grad of inverse Laplacian. The grad of inverse Laplacian, clearly its divergence gives us F. And the Helmholtz solution, if F is in L2, the Helmholtz solution will be in H1. However, H1 need not be in L infinity, in two-space dimension. In fact, here is a counterexample. If we take F to be the Laplacian of this logarithmic, of this function with this logarithmic singularity at the origin, it is in L2, and for theta less than 1/2, its Helmholtz solution is not uniformly bounded. So right now, the Helmholtz solution does not solve our problem because there are L2 objects that we cannot represent as divergence of uniformly bounded something, at least not by Helmholtz solution. So if not Helmholtz solution, let me reformulate the problem. Notice that Helmholtz solution gives us automatically that the curl is 0, but I didn't ask about the curl. So let me reformulate my little question. The question is the following: can we gain uniform boundedness on U at the expense of giving up that the curl should be 0? The curl being 0 is the Helmholtz solution. I don't want it. I want to give up the curl being 0 and to gain uniform boundedness in order to solve this little problem, in order to follow the recipe that I offered from going to solve ROF to the obstacle problem. And now we remain not clear. The question is, do we have any other suggestion how to solve this little problem of representing an arbitrary L2 object as the divergence of something in L infinity? So we have to think. I don't know if anyone wants to give me an answer. And after some thinking, one realizes that the question is not as trivial as it seems. In fact, at this point, it is clear once you think about it that the problem is very difficult, so much so that at this stage, I completely abandoned the ROF and image processing. I do not care anymore about image processing. I care about this problem. So this problem now, everything was just a motivation for this problem. So let me reformulate. Is it true that any F with 0 average can be written as the divergence of something in L infinity so that we get this kind of bound? This is the question. Is it true? The answer for that question was provided in a paper of Bourgain-Brezis. And this brings me to Bourgain-Brezis, a paper from 2003, which is a must-read paper. And the answer to this question has two parts. The first part says, yes, it is true that any F in L2 can be written as the divergence of L infinity solution, an L infinity solution. But there is a second part, which is interesting, and it says that the construction of this U from F cannot be done in a linear fashion. What does it mean? It means there is no linear operator mapping L2 to L infinity, which will be our solution operator, none. Such that the div of K of F will recover F if K is linear. There is no such operator. So this starts to be interesting. It means that the problem, which I will now refer as the Bourgain-Brezis problem to simplify matters, it has a solution, but its solution must be nonlinear, which of course is intriguing. What does it mean that it must be nonlinear? This is a linear equation. Well, but it has a solution which is nonlinear. Let me first of all quote the statement from Bourgain-Brezis, why there is no such linear, because it's actually rather simple to show why there is no linear solver. If there was linear solver, we can always average it over all possible translations on the torus, and then we will get, instead of an operator k, we'll get operator k twiddle, which will be translation invariant. It will compute these all translations. If it's translation invariant, it means that it's a multiplier. Multiplier means that if it operates on the exponentials, then it gets back the exponentials with some multiplier. This is the sort of the symbol, lambda 1, lambda 2. This must be a 2 vector, right? And it maps L2 to L infinity, and therefore by duality it will map L1 to L2. The special thing of mapping something from L1 to L2 is we know exactly how to characterize these operators in terms of the symbol. If we have something bounded from L1 to L2, this is true if and only if the symbol belongs to is square summable. This 2 vector is square summable. But this is impossible. The reason is, if the divergence of K is the identity, this means that the sum of nj lambda j equal 1. This is just the dual statement of div k equal 1 identity. So the sum of differentiation times k is the inverse of the divergence equals to 1, and therefore by Cauchy-Schwarz, the L2 size of lambda is greater than 1 of the L2 norm of n, and the L2 norm of n is just barely, but it's not in L2. So there is no linear solution to our problem. Nevertheless, there is a solution, even though it's not linear. And the question is, how do we know that? It follows that there exists bounded solution for the Bourgain-Brezis problem, and it follows by duality argument from Gagliardo-Nirenberg inequality. In fact, to be precise, here's the Bourgain-Brezis statement: there exists a solution, and this is equivalent to a dual statement. So you see the L infinity goes with the space of measures, the divergence with the gradient, the L2 with itself, and this estimate holds, and this is the Gagliardo-Nirenberg inequality in 2 space dimension. And if and only if this estimate holds, then there exists a solution. Why? It's easy to see when we go from right to left, namely, if there exists a solution, then this estimate holds. I'm not interested in that. I'm interested in the other direction. If this estimate holds, which it does, then indeed there exists a solution, and this is a consequence of the closed range theorem. It turns out that the closed range theorem gives us, of course, existence of solution, which not always need to be linear. This is a non-constructive proof, and here we finally come to the main topic of this talk. The main topic of this talk will be a constructive solution for the Bourgain-Brezis problem. It is not only constructive, I will give you now the precise formula for the solution of the Bourgain-Brezis equation. And it's an explicit construction which involves multiscale representation. So the solution for a Bourgain-Brezis problem, capital U, will be the sum of these basic molecules, if you want, to atoms. And they are constructed in a hierarchical manner in the following way. If you have the first j terms, and therefore you have the partial sum u sub j, then I will tell you how you construct the next term, little uj plus 1, and it is given by the following minimization. So you minimize the L infinity, and you take lambda j times f minus the divergence of all the terms that you know, minus the divergence of the terms that you do not know in L2. So this is the variational statement that we saw before. The only trick here is that the lambda j's have to change from one step to the next, and they have to be dyadic scales. If we take the lambda j to increase dyadically, it follows that these atoms at step j are uniformly bounded by 2 minus j, and therefore the sum, that is the infinite sum, capital U, is indeed uniformly bounded. And here is the explicit construction for the Bourgain-Brezis problem. And this is actually, now I start my talk. So the question is, where did I get this hierarchical construction? Why is it true? Why do we need hierarchical scales? And besides, how do we get into all of that? Okay, so let me, so this is it. This is the end of the introduction and the beginning of the lecture. I have to see, yeah, okay. So in order to see the hierarchical solution for this two-dimensional Bourgain-Brezis, let's see how it works out. So let's try to solve it. What we try to do is to find the minimizer, which is the solution is uniformly bounded, because that's what Bourgain-Brezis is looking for. And we try to minimize, of course, this residual, the difference between F and the divergence of U. If we are lucky and the residual is 0, then we are done. But in general, we are not lucky, and we will have residual, which I call R1. And after the first step, we'll get that F is the divergence of something uniformly bounded plus a residual. It turns out that if lambda 1 is sufficiently large, then there exists such a minimizer. And moreover, the minimizer is characterized by this property that the total variation of the residual is given by 1/2 lambda 1. I should make a general comment here, which is very important. All these variational statements that I'm looking at will have a specific characterization, and the characterization is always not in terms of the minimizer, but in terms of its residual. So here, the residual is 1/2 lambda 1. Well, the next step is therefore to do the following. If the residual is bounded variation is inside L2 because of the Gagliardo-Nirenberg inequality. It has 0 average, and therefore this residual is also in L2, and therefore we can use the same minimization. Now we zoom into the residual. You see, I replace F by R, and I do the same thing as I've done before. The point is, now I take lambda 2 greater than lambda 1, and of course I will get that R1 is the div U2 plus R2. So after 2 steps, I will get that F is the div U1 plus the residual R1, and now it will be the div of U1 plus U2 plus another residual, and now the residual will be smaller because it is of the size proportional to 1/2 lambda 2, which is smaller than 1/2 lambda 1. So we get an improved approximation. So the idea is now clear. Let's reiterate again and again. Each time we reiterate, we will get zoom into the residual and extract more information. And this is exactly what is written here. It's exactly what I told you before. It's the general refinement step. What is the refinement step? You have a residual Rj, you find the next Uj plus 1, and once you find the Uj plus 1, then the Rj consists of the divergence of Uj plus 1 plus the next residual. And this refinement step is keep being iterated. That's what I wrote to you before. So clearly, we will get now that F is the divergence of partial sums plus residuals, and the residual will tend to 0 because the lambda k will tend to infinity. So F is the divergence of something. This is not the question. The question is whether this something is uniformly bounded, and here we have to be careful. Any questions? Okay. So now we come to the delicate matter. Is it true that this something, this infinite sum, is uniformly bounded? Let's see. So the idea is this. When we do this refinement step, and we get that the residual now is decomposed to a divergence plus another residual, of course, this minimization is the minimizer, the best possibility. So that's what is written here. Uj plus 1 in L infinity plus lambda j plus 1, Rj plus 1. That's exactly this iteration. It's clearly the best. So it's better than if we choose here U to be 0. When we plug here U to be 0, this term drops out. We get lambda j plus 1, and we get Rj L2 squared. The L2 is bounded by the total variation squared. The total variation, we remember, is lambda j squared, and we get the ratio between lambda j plus 1 divided by lambda j. And here's the reason that we take dyadic scales, because this ratio is now of order 2 to the minus j. And now we conclude that the size of this molecule is precisely of order 2 to the minus j. And therefore, our infinite sum is uniformly bounded. And in fact, when you do it correctly, you get, it depends on this free parameter, and we end up with something of the order, which is the L2 of F. So this is it. So this is the hierarchical decomposition for the solution of the Bourgain-Brezis, which was introduced in this paper from 2016. Before we continue, because clearly this methodology is much broader, and I'm just presenting here it as an excuse for opening the whole scope. Let us see, first of all, how this hierarchical decomposition looks like. This is a joint work with Chang Ten, an old work. And in particular, let's look at this Nuremberg solution, which we know that the Helmholtz solution will not be uniformly bounded. So this is the F that was mentioned before. And this is how the Helmholtz solution looks like. And this is how this hierarchical decomposition looks like. There's a lot of numerical difficulties I will not describe here, but you can see that there are some numerical artifacts. But what is really important is when you look at the ratio between the L infinity and the L2, you can see that while the Helmholtz solution has a slight growth, it's a logarithmic growth, the hierarchical decomposition, which I described before, remains uniformly bounded. So indeed, there are issues with the computation of n-hierarchical minimizers, and they were outlined in this old paper. But I will come back to describe this as well later on. But first of all, we at least enjoy watching a solution which does not blow up logarithmically, and it must be nonlinear, because that's what Bourgain-Brezis told us. Okay. Now, there are several implications from this decomposition of Bourgain-Brezis. I mentioned, due to time, I will not mention everything. Here is just a small example. Let's assume that you have a vector field whose divergence is small in L2, less than epsilon. We know that there is a divergence-free, it follows that there is a divergence-free field set which is close to W, but it's closed in L infinity, not in H1. The usual approach is in H1. The claim here, I replace the H1 by L infinity. There are many other implications. I mean, so this is the proof. There are many other borderline estimates that I will skip due to time. And what I would like to do now is to approach the general setup of the hierarchical decomposition I just told you. So what is the general setup? It's clearly much more general than just the specific examples I brought you before, which was motivated by ROF. So here's the general setup. Given a function in LP, we want to solve the linear equation LU equals F, where we insist that U will be in some borderline regularity space X. How do we solve it? We solve it by just a general Tikhonov regularization. Namely, we find the minimizer, where the minimizer asks us that the minimizer itself will lie in the space X, and we take a lambda parameter, which actually is a scale, of the residual between F and LU measured in LP, because we are given that F is in LP. And from this is a general variational statement that you can see across so many fields. I usually at this point raise my hand and ask, what is lambda? And the answer usually comes, well, it is a tuning parameter. I claim it's not a parameter, it's a scale. And you can see it from the hierarchical decomposition. The idea is that once you do one step, then you do this refinement step. You take the residual with a refined scale, lambda j plus 1, you get the next approximation, and then you iterate again and again, you get the partial sum, and then if the residual tends to 0, you get a solution to LU equals to F. Of course, the main issue is to verify that U remains in the space X, but we will discuss it, we will come to that in a second. So here are one example. The div U equals F problem corresponds to the case that L is the div, and the spaces X and Y are L infinity and LD. D equal 2 is what I discussed before. So this is the div U equal to F. There is another problem, and believe it or not, I go back now to image processing. The second problem I would like to mention is the case when the spaces X and Y are BV in L2 and L is the identity. In this case, we decompose F in L2 to something which is total variation bounded plus a residual, and indeed this is the original ROF. So in fact, I come back now to image processing because this procedure of hierarchical decomposition was introduced in the context of image processing and later on was imported in order to solve Bourgain-Brezis. So what does it mean in the context of image processing? You are giving me an image F, let me use this terminology. You are giving me a possible blurring operator L, and then I try to minimize the total variation of the minimizer plus a set of scales times the residuals, but now the residuals are measured in L2. So in fact, the origin are images, and this is the reason for the language of trying to zoom into the residuals. And it goes back to even older works from 2004 and 2008, where we start with an image and we do the refinement steps. And in case of denoising, the operator L is simply the identity, and we get basically hierarchical decomposition of ROF when the image is in fact is the sum of different molecules, not just one term. And you understand, for example, in deep blurring, what happens is we take the image, we do one step, then we take the residual, we get the second step, we take the second residual, and so forth and so on. So you understand that this is a much broader spectrum, much broader framework, and we can talk with this kind of language. What we observe is F, which is approximately an operator operating on a sum of scales, and the deblurred version allows us on these finitely many scales to invert the operator, which is otherwise on the whole space is non-invertible. And in order to do this, this requires this kind of a dual bound corresponding to Gagliardo-Nirenberg that we had before. So there are many other issues regarding the implementation of this kind of image hierarchical decomposition, which I will not get to because I do not have time. But the nice thing here is that now we can watch the hierarchical decomposition on actual images, and we can judge for ourselves how they perform. So let's see, how does it work? So we have to find this kind of minimizer, the total variation of u plus lambda j plus 1, the residual from the previous iterations times the L2 of u. How do we find the minimizer? Essentially, we look at Euler-Lagrange. And let me write to you what are the Euler-Lagrange for this minimizer. It's this curvature term, the uj plus 1, the minimizer, satisfied that uj plus 1 minus a coefficient times the divergence of the normalized gradient equals to the previous residual, which happens to be that. So we start with F, and then we simply iterate this star relation, and we get the molecules uj, and in fact it follows that every function in L2 can be decomposed into these image molecules, which are in BV, plus a lower order terms in L2, and each BV size of uj is precisely of the order 2 to the minus j. There are many other side issues that, again, due to time, I will have to skip because I'm trying now to together with you to see how it looks. So what does it mean that we zoom with this hierarchical decomposition? It's just in front of you. So this is an image of Barbara. This is the clean image. And what you see is the first iteration. In the first iteration, by given some scale lambda 1, you clearly see the rough scales of Barbara. What you see here is U1 plus U2. So we choose dyadic scale, and then we add another slice, and then this is what you see here. This is the third slice added. This is the next slice, and finally we recover the image itself. And the only thing that we do here, we start with this image, F, that you see here, and we iterate this Euler-Lagrange equation. The important thing here is that now we know that this image is, in some sense, a direct sum of different scales, precise scales, and the scales are quantified to be, in this case, the order of 2 to the minus j. So we decompose here. Of course, I show you here the partial sum, but we decompose the image into separate slices. Okay. Here's another example for decomposition of an image of a galaxy in 10 steps. This is the galaxy. You can see here edges. You can see here what you might call texture, and it will be interesting to see how it's decomposed in different slices, and that's exactly what you see here. This is slice 1, 2, 3, 4, and you see how each step, when we zoom into the residual, we essentially recover more and more edges according to the ROF, and eventually we recover the image exactly because it has no noise at this stage. Okay, So we can, for example, distinguish between the larger scale, the smaller scale, and so forth and so on. Now, I should mention that the ROF decomposition, where we take an image and we decompose it to the main feature and the residual features, is part of a general framework of so-called U plus V decomposition of an image. And the U plus V decomposition is dictated by the spaces. Before it was L2 and BV, there are many other such pairs. I will not cover everything in image processing. Let me just mention here, if you take BV and L2, this is the ROF. If you take BV and L1, it's another kind of decomposition. If you take the subspace of BV, this corresponds to Mumford-Cha, to Osher-Vese, and so forth and so on. So there are many pairs. For each pair, we can have this kind of hierarchical decompositions. And of course, there are other decompositions which do not fall into this category. I do not want to forget them. For example, wavelet shrinkage, where you take the substantial, you do some thresholding. This will be the U, and then the rest will be the V. Okay, and this related to another thing of Osher and his group, to what is called iterated total variation with Bregman iterations and so forth. It requires really a lecture by itself, so I will have to skip and to move on. And what I would like to show you is, just as an example without justification, a Mumford-Cha decomposition. If you remember, this is a different kind of space, not space BV, but SBV. And the decomposition consists of U, V, and then there is a third component, W, which is the lies on the support of the edges. So here's the forehead of Barbara. And what you see here in hierarchical decomposition description, just these detectors, the W, not the U, not the V, but those that live on the edges. And you literally see the cartoon being drawn in front of you out of the edges, because you start to see how it is being enhanced, and finally we recover what we have there. Okay, here's an example for a colored image, in which case the function f is a tree vector. And we start with, I would say, something which looks like, it's not an edge, it's texture. But a texture is nothing but a collection of edges if you zoom close enough. When you are far, this is what you see. And when you refine the scales, you see more and more information until you recover the image, and the same thing happens here. So the story here is that by refining the scales, you can get the image with the details that you need. Okay. So let me move now to another aspect about evolution in inverse scale space. This is a series of works that followed with Prashant et al. During these years. And the idea starts with the following, with the question. Let me ask you, I mentioned before that images, they are a collection of pixels which are scales from 1 to 255. And I always had a problem with what is 1? What is 1? Why 1? 1 measures what? So since I did not know, I wanted to now introduce intensity quanta, which I will call tau. Tau is a small number. So tau will replace the 1. So instead of tau, we have 255 tau, but it could be anything. So let's see what will happen if we will rerun the whole theory from scratch. The answer is that now we will represent the image as tau multiplying these, say, edges, plus a V part, which is the residual or the unimportant part. And the minimizer will take this form. Once we have the minimizer, then if you remember, we have these Euler-Lagrange that we have to iterate, and they look exactly as we see here in the box. And you do not have to pay attention to the details, except for one thing. Now I notice that when I look at this refinement stage, whatever is written in this term is exactly the next term written here. So clearly, it calls for a telescoping sum. And that's exactly what we will do. Let's do a telescoping sum of this refinement step. Here it is. So we get that the sum of the uj multiplied by tau, the small intensity quanta, the small scale, minus f, it's the first term here, is given by the last term. Clearly, by letting tau go to 0, we get a new integral differential equation, IDE, in the intensity space, which tells us that the integral of us ds minus f is given by this curvature term. So we have to solve these integral differential equations, and this replaces the iteration I just mentioned before. So this is the IDE, and the idea is that we start with the solution at t0, this is the scale, and then the observed, and then we move into restoring the image that we want to. I will not mention reference to Perona Malik and many other things. Again, due to time, I will just focus on this image. So here's the blurred image at scale, intensity scale t equal 1. And here we solve this IDE in the inverse scale space from t equal 1 to t equal 10. And then we move from this image to that image in this fashion. Of course, in order to do that, we have to agree what is, because here there is a blurring, there is no noise. So we have to agree what is the blur operator. So for example, here's an example when there is a blurring operator, which is modeled by convolution with some Gaussian, with certain parameter sigma. In this case, we get this kind of integral differential equation. There are many details that I have to sweep under the rug. I'm sorry. I just wanted basically to share with you what is the main idea. And the main idea is this hierarchical decomposition. Here it is on a continuous scale. Here is another example when we do this IDE and the space is now on the top is BVL2. We can do it in BVL1, and we all know that there is a difference between BVL1 and BVL2. And you can see that the recovery from the blurred image to the exact image is different between the L2 on the top and the L1 at the bottom. Notice that these dots are not recovered there. Okay. So hierarchical construction may serve us as a universal solver. What did we see? We addressed it for the problem of Bourgain-Brezis. We actually initiated the whole story in terms of images. So let us revisit what is the general framework. Given f in LP, we find the solution for the problem LU equals to f. And the solver is simply by iterate these canonical iterations. And the main theorem says that if L star is injective, if we have this kind of a priori estimate corresponding to Gagliardo-Nirenberg, then indeed this problem admits, we know by the closed range theorem, admits a solution, but in fact here is a constructive way for accessing this solution. It's the hierarchical, call it hierarchical solution given by the sum of the UJs, and you know how it's constructed here, and this U in the space X is indeed bounded by the LP norm of F. And the proof is exactly what I showed you at the beginning of this lecture. Essentially, the X size of the J molecule here is bounded by the residual to the power P, and this residual is bounded by lambda J plus 1 divided by lambda J to the power P prime. P is greater than 1, and this quantity is uniformly summable, and that's the end of the story. Okay, fine. So equipped with this kind of hierarchical construction, we are now becoming a little bit more aggressive, and we would like to solve some other problems. So let's see. We know when the L is the identity, we decompose an image, an L2 image, into BV scales. That's what we've seen before. Where L is a convolution with some Gaussian kernel, namely blurring, we get a representation of the solution of the image, the clean image, again in terms of some BV scales given here, as long as we have this a priori bound. What about Bourgain-Brezis? When we have F in LP, then we get a solution in LP prime, and we know that if the solution here is in LP, then we can take the Helmholtz solution. We get a solution. We will get a solution U in W1P. Sorry, this is because we have this duality estimate, which is clear. If F is an LP and you're looking for a solution not in W1P, notice F in LP, not a solution in W1P, but you look for a solution in LQ, again, you look at this duality estimate, and this duality estimates, Q is the Sobolev index, will guarantee that there exists a solution. There's only one case which is critical, that is when P equals the dimension. Before we take the case D equal to 2, when P equals the dimension, then Q equals infinity. It fails to satisfy this inequality. And this is the critical case when there is no left inverse. This is the problem of Bourgain-Brezis in general D dimensions. Namely, given F in LD of TD, find a uniformly bounded solution. So in this case, it's critical and it's characterized by a kernel that does not have a complement. Okay. So let's continue now with the examples, and let's finally get what is the important result of the Bourgain-Brezis. I didn't tell you what is really the important result of the Bourgain-Brezis paper, and I'm now coming towards the end of the lecture. I believe I still have 5 minutes. Am I correct? Or okay. So here's the essence of the 2003 remarkable paper, really a masterpiece of Bourgain-Brezis. Let's focus on the two-dimensional problem again. We remember that if F is in L2, clearly we have the Helmholtz solution, which is in H1. We were looking not for a solution which is in H1, we were looking for a solution which is in infinity, and this was the beginning of our conversation. The question is, can we find a solution which is in both, in L infinity and in H1? Because the Helmholtz solution does not solve the infinity part. The infinity part is not clear that is in H1. So can we find a solution that is in both? Well, we can find a solution in both if and only if the corresponding dual estimate holds. What is the dual estimate? The dual estimate says that the L2 norm of a function should be bounded not by the L1 of the gradient, the total variation of G, but the L1 plus H minus 1. Namely, we should decompose the gradient of G into two pieces. One is bounded in L1, the other in H minus 1, but neither of these pieces should be a full gradient. So what about this estimate? What is the name of this estimate? Well, this estimate was not known. In fact, if we want to go from the 2-dimension to the D dimension, the corresponding estimate will say that LD prime, this is the D dimension, should be decomposed accordingly into L1 and W minus 1 D prime. What about this estimate? Do we have this estimate? If we have this estimate, then and only then there exists a solution for the enhanced Bourgain-Brezis. So here comes a delicate point that I would like to, I have to clarify so that Chaim Brezis will not criticize certain things. Let me explain. In order to solve this inequality, we require to have this decomposition of the gradient into two pieces, and it's not known if this estimate holds. And it was solved by Bourgain-Brezis. The question is, so how Bourgain-Brezis showed that star holds? They did not. They showed that star holds simply by constructing a solution for their problem, namely a solution for d view equals f, where u is in the intersection of L infinity and H1. This construction is extremely intricate, way more intricate than can be described here, specifically tailored to this problem. But once they have a constructive proof, of course, it follows that star holds. As much as I'm aware, today, the only direct result for this estimate is known for d equal 2, but the question for d greater than 2 remains open. But still, star holds. Now, since star holds, I can come now and use the argument of Bourgain-Brezis and claim that also the hierarchical construction holds, because we know that this dual estimate holds. Therefore, it guarantees that if we use this refinement step that I showed again and again, this time at the space L infinity intersect W1D, these iterations will converge to the desired solution. So in some closed circle, they prove it by construction, therefore there is estimate holds, and therefore the hierarchical decomposition works. And I should say that there are other critical problems that they mention in the paper. For example, they solved the case that when F is in L3 in T3, then it can represent it as the curl of uniformly bounded fields. I should mention a couple of more statements here, but due to time, okay. So let me just mention one thing, that in the two-space dimension, there is a much simpler two-step hierarchical construction. And the reason is the following: when we find the minimizer after one step, this minimizer, the residual, is in BV. A function in BV is not just in L2. In fact, it is in slightly smaller space than L2, called the Lorentz space L21. And believe it or not, in space L21, the Helmholtz solution is in L infinity, because the gradient of minus n of the inverse Laplacian, this kernel belongs to L2, to weak L2, and weak L2 pairs well with L21, and therefore we get solution in L infinity, and therefore we need only 2 steps to do the hierarchical decomposition, which is exactly what we did, and therefore we got a much better representation of the solution, which you can see here. So here you have the hierarchical decomposition, a 2-step version. Of course, it's much cleaner. This goes back to this work I mentioned before. And in fact, in the 2-space dimension, together with Albert Cohen and Devor, we can show that one can solve the Bourgain-Brezis in this special case, even in 1 step. But this is a very special case, I must admit. Let me conclude that there are some open questions which are very interesting. For example, can we generalize the Bourgain-Brezis to data which is a positive measure? How one computes the minimizer? There are many minimizers. Should we choose the one which has the smallest curl, and how do we do it? And in general, we have a new paradigm where whenever we have the Helmholtz part, we exchange the 0 curl but uniform bound of U. And there are many other examples when we can use this hierarchical decomposition. Here is a recent application for basis pursuit. This is the Lasso algorithm. 1 step of the Lasso algorithm, we have a vector which is sparse, a long vector which is sparse vector U. You have a matrix which satisfies the restricted isometry property, which is a band matrix. And then depending on the properties of A, one can recover by this variational statement, the minimizer recovers approximate solution for the sparse data, and by iteration, so this is rather recent work, by iterations we can recover the sparse solution exactly. Okay, so this is the summary, and thank you for the attention. And let me refer you, there is a series of papers. I cannot cover everything, but in particular, I would like to refer to this work of Modin, Nachman, and Rondi in quite recent work, where they generalize the hierarchical decomposition into the nonlinear setup. Thank you.
If people would like to unmute and ask questions. Any question? Well, at the beginning of your talk, the first thing that occurred to me when you were discussing in connection with the basically 2-dimensional photographs and images, everything was in 2D. And I wondered, well, what happens in 3D? Because things like curls and divs are rather different in 3D. But then you explained to us that much will hold in 3D, but not everything.
Yes, so let me say a split answer to your question. First, when you have a colored image, then yes, you map, let's say, a square basically into R3, and of course the R3 here is the 3 components of the color.
Mm-hmm.
Okay, so this is one thing. But this is not to be confused with the fact that or maybe I do it, you know, that images are in L2. It's still, okay, so there is still, so there is an intimate relation here between L2 and the fact that I map the 2-dimensional base, right? Because if something here is in L3 and not in L2, then it does not go with the space of bounded variation. I mean, there is a delicate relationship here between bounded variation being the correct subspace of L2. So I don't know if I
in 2 dimensions.
There is a delicate matter. So if this would not be L2, then this would not be BV, and this goes back to ROF. So there's a very delicate matter here. But I mean, as far as colored images, these are just function in L2 with 3 components.
Mm-hmm. Mm-hmm. Okay, thank you. So, other comments, questions?
I have a couple of questions. Maybe the first one is the easy one. So this is all on the torus, right?
This is Wojtek asking?
Yes, yes.
Yes. Okay, so just to simplify matters, I made it on the torus, but the truth of the matter is everything is actually on a finite domain with the Dirichlet boundary conditions.
I see.
With the Dirichlet boundary conditions, yeah.
I see.
Yeah. That's the precise statement, yeah. The highly nonlinear structure of this talk, where I started with images, go to Bourgain-Brezis, I come back to images, and then I started and forced me to do some shortcuts, which are a little bit unorthodox, but yeah. So yes, no, the general problem is solved really with the Dirichlet boundary conditions.
Right, but the proof you showed by Bourgain-Brezis was based on the fact that you can represent some linear operators as multipliers. And that's on a that still works in the Dirichlet boundary conditions?
That's a good question. Actually, they have two proofs. No, it doesn't work because if it's okay. So now I don't. Okay, so so it goes like this. First of all, they have two proofs. I put this proof because only this one I can show here. The other one is just a little bit too abstract for me. Does it work on the non-periodic case? Yes, because the only thing that is the only trick there, I mean, I've never seen anything like that, is when you have a linear operator, you have to average it over all translations in order to get something which is a translation. And I think, does it work when you have zero Dirichlet? I don't know. I mean, does continuity comes into? I never thought about it. I never thought. I just so much enjoyed the ability to prove something so unorthodox that I included here in the case of periodic. I never. Because if you have it zero, I mean, now the question of oddness. I mean, I don't.
Right.
Right, it's a question of extension because you need periodicity. Otherwise, you have to make an operator here so that it is a multiplier. Yeah, that's a delicate point.
I see. I have a couple of more questions, if that's okay.
Sure.
So you have when you were showing these pictures of the hierarchical solutions, right? It seemed to me that when lambda j is increasing, you get final picture that somehow reminded me of the Parseval identity. When you is there any relation that you would see with? So if you approximate function by just Fourier series, right?
Wojtek, let me tell you, I cannot but smile. So yeah, I cannot but smile. Let me explain to you why I cannot but smile. So so the statement is the following. Every function, by the way, this statement I did not prove. Every function in L2 can be decomposed into this infinite sum. And of course, the corresponding statements are in general by this hierarchical decomposition. So I was able to prove it with an inequality for f's, which are a slight subspace of L2. And this proof, I think you can find in the paper that I just mentioned of Nachman and co-workers. And also it was proved by Mario Millman. And I was very pleased by that because, of course, I looked for a long time, but what I call this a non-linear Fourier expansion. And this should be the non-linear equivalent of Parseval, right? This is exactly it. It's equality. It's very important. And basically what it tells you is that each molecule here lives precisely at scale lambda j. And this is a lower order term because the L2 is dominated by the BV. So once I saw this part, if you say Parseval, of course, you should ask, what is the inner product? Is there a non-linear inner product? I spent quite some time on that. More than quite some time because I wanted to gain some insight. Essentially, I'm telling you every function can be decomposed into the sum of the UJs. And this is a different decomposition than we are familiar in harmonic analysis because it's a nonlinear decomposition. And the advantage is that each piece lives in its own scale. So I must be doing something that others cannot. I didn't get anywhere, I'm sorry to say. I tried, but that's the reason I'm smiling. So it reminds me that this is an unfinished business.
Yeah,
there must be something here. There is an inner product. It is true. There is an inner product between F and G. You take F and G, you make a hierarchical decomposition, and then you take the inner product of the corresponding scales. Makes sense. Well, you have to do it in a proper way. And as a result of this, you get this, you see, there's a long story of, you get this nonlinear Parseval. And of course, I was shooting to get something that the others cannot, but I was not quite there. I'm missing something. And then I other things came up, and that's it.
Sure, I see. But this is very interesting. Thanks for sharing.
I cannot agree with you more that this decomposition is very interesting.
Mm-hmm. Mm-hmm. I have one more comment, if that's okay.
Sure.
So at the end, you have mentioned that the problem of uniqueness, that there's many solutions that you can have.
Fantastic. Thank you for the questions. I mean, you're just hitting exactly, you're just hitting exactly all the points that we in this is not just unfinished business. This is really opening okay, so let me, I didn't even let you finish, but let me tell you what the story is.
Sure.
So let me be very concrete, okay? Let's think, for example, of the incompressible Euler equations. Okay, so when I say new paradigm, what do we have in the incompressible Euler equations? We have a force. The force, we have a force F, and the force F is, if you want, a Lagrange multiplier, so that we can enforce the incompressibility. Okay, I would like to formulate it in this statement because now comes the substatement. We will say that the force is not just only a force, namely not only that the divergence of the force here equals something which comes by incompressibility, but we say that the force has zero curl, i.e. the force is a pressure, the gradient of a pressure. Now, what I'm suggesting is, well, instead of the zero curl, let's assume that it's not the gradient of the pressure, it's some force, but the force is uniformly bounded, which would imply that the velocity is bounded. Okay, so what's wrong with this picture? Nothing. It's a very viable picture. The point is that now we will have a curl for this force. There are many solutions for Bourgain-Brezis. So the question that I'm asking here is, out of many solutions, can we find the one with the smallest curl? One whose curl is most of the time zero. It cannot always be zero because of the result. I don't know the answer. I don't know the answer. This is a measure theoretic question that will tell me how to select this new paradigm. So instead of Helmholtz, I will take something which is uniformly bounded, but with a minimal intervention to the curl, rather minimal intervention for the uniform boundedness. So now comes the question, what is more accessible, uniform boundedness of the velocity or the curl being zero? That's basically what. So you can see that, of course, there's another, you were asking a question that is very much on my desk, but
I see.
I don't. It's just one example which I wanted to bring. You can think now of many other problems where you take the, shall we call it the Helmholtz paradigm, where the curl is zero, and you really trade the curl being zero, i.e., whatever field you're talking about is the gradient of something. You trade it by uniform boundedness.
Mm-hmm. Mm-hmm. So let me add the comment that I wanted to add. That's okay. So apparently you can construct the vector fields that have zero divergence and are almost everywhere in absolute value to be one. And you can do it using convex integration. In fact, you can show that these vector fields are dense in L2. And that again is actually very interesting. I wonder if you have any thoughts on that because it has links to Euler equations. There's lots of work.
Can you repeat your question? I'm sorry. I don't mind. I mean, continuing. I mean, can you repeat your question because you said convex integration, and I should say something.
Right. So I was just saying that you can use the method of convex integration to quite easily prove that the problem of the following form, that you have a given subdomain, and you want to find the divergence-free vector field everywhere, that on this particular subdomain, has absolute value equal to 1 almost everywhere. You can do it quite easily using some convex integration.
Convex integration, that's correct.
Yes, and that has links, as you know, to other equations.
That's absolutely correct, because I think we have heard the same lecture by Sekeleidi, at least I remember hearing the lecture by Sekeleidi. That's a very interesting remark that you make. I just want to say that Sekeleidi and other people, and I myself, you realize that this has a general tone of convex integration, because what happens with this kind of hierarchical decomposition is that I recover the equality, and not from one side, but modulo a small error that I continue to correct again and again. I never thought of actually taking the example d view identically 1 and compare it. And the solution is, okay, d view equal to 1 and the u is...
So it's d view equal to 0.
D view equal to 0.
The distributional sense, but the absolute value of the vector field.
That's correct. And the absolute value of u equals to 1. You know what, I should, first of all, thank you for the question. Thank you for the question. And that's a fantastic problem to try, because this is nice link. It's a fantastic problem to try in the context of this hierarchical decomposition. Now one has to think, of course, what space is X and what is the variational statement that we are going to discuss here. That's the only problem. So the idea is that d view equal to 0 when absolute value of u equals to 1 almost everywhere. Yes, I remember that. Thank you. Okay, I will try it. Yeah, that's it.